it. Turn on volume. Welcome everybody. Sorry, I'm a minute late here getting things going. I'm sure you guys will forgive me. Let me get my stuff out of the way. Oh, that's interesting. If you were saying words, I accidentally had my headphone off out of its charging station. So volume was probably coming through that, which means I wasn't hearing you if you were saying words. My cat will need to be let out in a minute here. She is fickle. Yes, leave, go, hi. I'm sure she'll come back and start yelling outside of the door to let her back in, but yeah, that's how cats are. Let's see here. Sorry, it's just something from a coworker here. We're going to do these problems on the board. I thought they kind of looked interesting. And then we'll jump into some more implicit. And then we'll do lots of related rates problems, which kind of have implicit. I mean, really everything is the chain rule. Implicit is the chain rule. Related rates is the chain rule. So chain rule, chain rule, chain rule all the time. Lauren is joining, but she doesn't seem to be in here yet. Let's see. All right, yeah, we should go. We should do the things. Or something else. Oh, I posted solutions to the quiz I gave you guys last week. I haven't graded them yet because I'm a slacker. But I'll get them graded and give you feedback on them if you want it. But if you had any questions about the quiz, they're a bunch of terrible chain rule problems. You can look at the solutions. I believe I wrote them out correctly. They are very ugly looking. I did not simplify them. So you should take a look at those if you have questions or concerns. But my goal is to get them graded today. Why is my speaker say the volume's not on? Oh, there we go. I put my headphone back on the thing, so it turned the volume back down. Smart, real smart. I mean, it's probably is smart. All right, enough of me just talking. Lauren, I don't know why you can't seem to get in. Seems weird. Oh, get in, I guess. All right. So this first question here, what is the 19th derivative of cosine x? So when someone asks you about a very high derivative of either sine or cosine, there's something happening here that they want you to do, which is that the derivative of sine and cosine cycle, right? The derivative of, so let me actually write on the other side of the board. So if your function is cosine, the first derivative is negative sine. The next derivative, f double prime of x, is, so the derivative of sine is cosine, so the derivative of negative sine is negative cosine. Okay. And then the third derivative of cosine, well, the derivative of negative cosine is negative sine, which is positive sine of x. And then the fourth derivative, so the derivative of sine here, is cosine of x. Then you've gone all the way through and gotten back where you started. So any further derivative is going to be just the next place in the cycle. So this is also going to be the fifth derivative of the function cosine. And this is going to be the sixth derivative. And this is going to be the seventh derivative. And this is going to be the eighth derivative. And so you can kind of see that every 4 times you do the derivative, you get back to the function you started with, if it's cosine or sine. So the 0th derivative, meaning the function you're starting with, is cosine. The 4th derivative is cosine. The 8th derivative is cosine. The 12th derivative is cosine. The 16th derivative is cosine, and so on, so on, so on. So if I want to find the 19th derivative, and I like to write it, let's write it this way. So if I'm trying to find, so this is one way of writing the 19th derivative. It's d superscript 19 over dx superscript 19 of your function. So I want to find the 19th derivative of cosine x. I know that every multiple of 4 worth is going to give me the same thing. So what's the biggest multiple of 4 that's less than 19? It's 16. So I'm going to write this as the third derivative, right? Because 19 minus 16 is 3. And then the 16th derivative of cosine x. So this says do the 16th derivative, and then after the 16th derivative, do the third derivative, right? So you're still doing the derivative 19 times. What's the 16th derivative of cosine? Oh, it's cosine, right? Because any multiple of 4 derivatives of sine or cosine is going to get you back to where you started. So the 16th derivative of cosine is cosine. So then I just have to take the third derivative of cosine x. Right, so the 16th derivative of cosine is cosine. And then the third derivative of cosine is, well, let's see. The first derivative is negative sine, the second derivative is negative cosine, the third derivative is positive sine. So the 19th derivative of cosine is sine. The 23rd derivative would also be sine. Any multiple of 4 plus 3 derivative would be equal to sine, whether it's the 19th or the 23rd or the 103rd. So when someone asks you the bajillionth derivative of sine or cosine, your job is to figure out, well, how many multiples of 4 are in there and then what's left over. So really the question is, if I'm looking for the 19th derivative, what's the remainder when you divide 19 by 4? Oh, the remainder is 3. So I'm really doing the third derivative. It's a little more challenging when it's sine of 2x instead of sine of x. So let me ask you guys a question. It's a very easy question to answer. What's the remainder when you divide 81 by 4? Everybody should tell me the answer here. You can write it in the chat. Thank you. One person. 1 is the answer, right? 81 divided by 4 is 20 with a remainder of 1. So if it was just sine of x instead of sine of 2x, we would know that the 81st derivative would be the same as the first derivative, which would be cosine of x. For sine of 2x, we have to be a little bit more sensible here. So let's see. The derivative, let me just write it. It's usually easier using functional notation. So my function is sine of 2x. The first derivative is cosine of 2x times 2 because of the chain rule. The second derivative is negative sine of 2x times 2 times another 2 because of the chain rule. Right? Every time you take the derivative of something of 2x, you're going to multiply by another 2. So the third derivative is going to be negative cosine of 2x times 2 times 2 times 2. And the fourth derivative is going to get you back to the function you started with, sine of 2x, except we're going to end up multiplying by 2 4 times. Well, I think we can see the pattern, right? The pattern is the usual cycle of 4 derivatives get you back to the function you started with, except we're also going to multiply by 2 to the 4th, which is, I think, not terrible to see that however many derivatives you take, you're going to multiply by that many 2's. So the 5th derivative would be whatever times 2 to the 5th. The 8th derivative would be whatever times 2 to the 8th. The 81st derivative of sine of 2x would be, well, the 81st derivative is the same as the first derivative, right? Because there's 20 cycles of 4, and then there's 1 left over. So we know that the 81st derivative, which I'm going to write like this, should be, well, the first derivative of sine is cosine. So it's going to be cosine of 2x times 2 to the what power? How many 2's are we going to multiply by? Well, how many 2's did we, or how many times did we take the derivative? 81 times. So that's going to be our answer here. And it'll be the same, right? Basically, whatever was multiplying by x here would be that number to the 81st power. If it was like a 3x or a 5x, you'd have 3 to the 81st or 5 to the 81st. So that's just kind of neat. People like to ask questions like this because they're not too hard to do once you know the trick, but you do have to kind of know the trick. Oh, interesting. It's weird. So on my participant screen here, I see that there's someone who looks like they're joining, but then they're also in the class. So I'm not concerned. It looks like everyone's here. I'm always like, oh, someone's trying to join. Oh, no, they're in the class. I don't know why it says they're joining, but that's okay. As long as everyone's here, we're good to go. If there was something else I wanted to say, just in general about life, maybe not. Let me do one thing here. You guys are all doing okay. It is week 7. After this week, there will be 3 full weeks of class, and then the week of finals. Yeah. So let's do a little bit more implicit. And then, yeah, I've got a couple implicit ones that are a little bit more challenging, and then we will move on. So let's try some implicit with some trig. Let's look at this one. What if we've got sine of x plus tangent of y equal to y squared plus 3x? And again, I want to find dy dx. So find, and you can either write it as dy dx or y prime, whatever you prefer. I usually prefer y prime because it's easier to write when I'm doing this process. So again, we're just going to differentiate everything. So the derivative of sine of x is cosine of x. The derivative of tangent, I don't know why didn't write, I mean, you can write parentheses or not. The derivative of tangent of y, well, the derivative of tangent of x is secant squared of x. The derivative of tangent of some stuff is secant squared of that stuff times the derivative of that stuff. On the right-hand side, did I really make this one that easy? I feel like it's too easy. Oh, that's supposed to be a y squared. I think I said y squared, but I wrote x squared. Sorry about that. That's supposed to be a y squared. Derivative of y squared, well, the derivative of some stuff squared is 2 times your stuff to the first power, I'm not going to write the power, times the derivative of your stuff, plus the derivative of 3x is 3. Okay, we've done all the calculus. The rest is just algebra. Group the things that have y primes together. Doesn't matter which side you want to pick. I'm going to pick the left-hand side. I usually pick the left-hand side unless I can see that bringing the y primes to the right would make like everything positive, and bringing them to the left would make everything negative. I prefer everything to be positive if that's an option. Here you're going to get some negatives and some positives, so just pick either side. So I'm going to write this as secant squared of y times y prime minus 2y times y prime equal to 3 minus cosine x. And if you want, in this step where you're bringing over the y primes to one side, you could also additionally do the step of factoring out the y prime if you really want to save on steps. Right, so I have secant squared of y times y prime minus 2y times y prime, and then I factor out the y prime to get y prime from secant squared of y minus 2y. And then the last step is to divide and get 3 minus cosine of x divided by secant squared of y minus 2y. Sure, I could ask that question. So then we could ask the question, what's the slope of the line tangent to this equation at the point 0, 0? Well, we've got the equation for the slope. We're just going to plug in 0 for sine, 0 for x and 0 for y. So plugging in 0 for x and 0 for y, we get that our slope is just y prime evaluated at 0, 0, which is going to be 3 minus cosine of 0 over secant squared of 0 minus 0. All right, cosine of 0 is 1. So 3 minus 1 over, and here's the nice thing. If you know cosine is 1, you also know that secant is 1 because secant is the reciprocal of cosine. So secant squared is 1 squared, which is 1 minus 0. So our slope here is 2. Alternatively, right, so I should back up a little bit. If we had been asked this question from the get-go, instead of doing all of this work to solve for y prime, we could have right here plugged in 0 for x and 0 for y. So just to kind of show you, right, that if you're just finding the slope of a tangent line, you're not being asked to find the derivative. After you differentiate both sides, you can just say, I'm going to plug in 0 right now. Cosine of 0 is 1. Secant of 0 is also 1. 1 squared is still 1. So 1 times y prime equals 2 times 0 times y prime is 0 plus 3. So solving for y prime, right, this is, right, if you were just finding the slope of the tangent line, doing all this work is probably more than you really need to do. It's much easier to just be like, I'm going to plug in right here and then say y prime equals 2. So I just want to reiterate, if you're just being asked to either find the slope of the tangent line or the equation of the tangent line, you don't have to actually solve for y prime in terms of x and y. You can plug in your point right after you differentiate both sides, which is nice. It's kind of weird being in a teaching world where I'm just kind of, I mean, I could try to elicit more interaction and get you guys talking, but my impression has been that that's not what people really want. They just kind of want to see me do examples. So it's a weird world where I'm just kind of talking to myself, it feels like. But that's the world we're living in right now. Good thing is I can talk to myself fairly easily. I do it all the time. So let's look at some more examples. Yeah, let's do this one. Yeah, that one seems fine. We are soaking your knowledge via osmosis. Don't worry. Okay, great. Speaking of osmosis, I feel like that's what Sarah said they were talking about in Biz 2a recently. X to the 4th, y to the 6th, minus 2xy equals 85. You know what? I think, so in the spirit of having you guys try something, I want you guys to try this one. So try this one using implicit. So we're solving for y prime completely. It's not like we're plugging in a point. So try solving this one. Differentiate both sides. You're going to have to use some product rules. So, and I'll give you, let's see, I'll give you 90 seconds to work this one out. And I need a stopwatch. So go ahead and start working on that one. I will be quiet for 90 seconds and then we'll talk about it. For those of you just joining, we're working on a problem for another minute. So go ahead and try this one. We're using implicit differentiation. Okay, it's been approximately 90 seconds. I'm assuming everybody tried their best. Certainly you could have done nothing right, but right, the value is in actually doing something. So hopefully everybody did try to actually do this. So here's how it's going to work, right? We're differentiating with respect to x, meaning we're assuming y is a function of x. it's implied, right? That's why it's called implicit differentiation, because it is implied that y is a function of x, even if it's not actually a function of x. So we're going to differentiate this using the product rule. We're going to get 4x cubed times y to the sixth, right? Derivative of this times the not derivative of that, plus, then we flip it, we do the not derivative of this times the derivative of this. And the derivative of y to the sixth is 6 times y to the fifth times y prime. Or I should say the derivative of some stuff to the sixth is 6 times your stuff to the fifth times the derivative of your stuff, right? You're always multiplying by the derivative of the inside stuff because of the chain rule. And then I would probably, yeah, I'm going to think of this as minus, and then I'm going to do the product rule for this. So I'm thinking of this as minus 2x times y. Specifically, I'm thinking of it as 2x times y. So product rule, the derivative of 2x is 2. Leave the y alone. So you get 2 times y. Plus the derivative of 2x is, sorry, not the derivative of 2x. I'm flipping it. I'm leaving 2x alone. Times the derivative of y, which is 1 times y prime, or just y prime. And I do need the parentheses here because I have to distribute the minus sign. Equal to, not 5, equal to 0, because we're differentiating both sides. It's always a good kind of idea to remember, if you do something to one side of an equation, you usually have to do it to the other side of the equation, right? You can't do something on the left and not also do it on the right. So if we're differentiating the left, we also have to differentiate the right. Now we're going to, I should distribute the minus, so yeah, I do need to distribute that minus sign, and I'm going to do a little bit of rewriting. So I got 4x cubed y to the sixth, plus 6x to the fourth, y to the fifth, y prime, minus 2y, minus 2x y prime. Might as well leave the y primes on the left, bring the other things to the right. And since they're already on the left, especially, let's go ahead and factor out a y prime. So from these two terms, if I factor out a y prime, I'm left with 6x to the fourth, y to the fifth, minus 2x, equal to positive 2y minus 4x cubed y to the sixth. I need to update my Zoom client. I keep getting this message to update. I'm like, oh, let's do it later. But apparently there are some features that are new, so I should actually do that sometime soon. Finally, dividing by this, you're going to get 2y minus 4x cubed y to the sixth over 6x to the fourth y to the fifth minus 2x. Normally you can't cancel much, if anything. You almost can, I don't think you can ever cancel of x or y unless it's a very special circumstance. Right? I could factor out a y from the top, but there's really no reason to because it won't cancel out with a y in the bottom. Similarly, I could factor out an x from the bottom. It won't cancel out with an x in the top. Here, I'm not going to, but you could actually factor out a 2 from the top and 2 from the bottom and cancel them. But we don't usually worry about that. All right, let's do 1 or 2 more, and then we will move on to other things. To related rates. Let's see here. I had a couple specific problems I want to make sure we get to. Yeah, let's do this one. So again, find y prime for x plus y to the fifth equal to xy plus x cubed plus y squared. This one has kind of an extra terribleness to it that we have to deal with. So let's differentiate the left-hand side. It's going to be 5 times your stuff to the fourth power times the derivative of your stuff. The derivative of your stuff is 1 plus y prime. Equal to product rule here. So it's going to be 1 times y plus x times y prime. Derivative of x cubed is 3x squared. Derivative of some stuff squared is 2 times your stuff times the derivative of stuff. Now here's the thing for this one. when you have essentially something times a piece that has a y prime plus a piece that's not y prime, you have to kind of separate something. You have to distribute. So you have to distribute this to each of these terms. Otherwise, we won't really be able to isolate y prime at the end. So I'm going to write this as 5 times x plus y to the fourth times 1, okay, plus 5 times x plus y to the fourth times y prime. And then the left-hand side is still, or sorry, the right-hand side is still the same. It's y plus x y prime plus 3x squared plus 2y y prime. And then we're going to bring all the y prime terms to whichever side feels convenient. So all those have to go on the same side. Let's bring them to the right just to do it differently for once. So, and I am going to factor out and bring it to the same side. So I'm going to have this plus this minus that. And if I factor out the y prime, it's going to be x plus 2y minus 5 times x plus y to the fourth. And then the y prime will be at the end. So I'm going to have x plus 2y minus 5 times x plus y to the fourth, all times y prime. On the left-hand side, I'm going to have this 5 times x plus y to the fourth minus y minus 3x squared. And then the last part is dividing by this grossness here. So we're going to get y prime equal to, let's see, I've got all this here. You don't want to multiply x plus y to the fourth. There's nothing to be gained from that really. So you get x plus y to the fourth minus y minus 3x squared divided by all this. X plus 2y minus 5 times x plus y to the fourth. Nothing cancels. You can only cancel things if you can factor them out from the top and bottom and then cancel them. Let's do one more and then we'll move on to related rates, which I enjoy talking about. Someone had it. I know I wrote down the question that someone had specifically, but I feel like I've misplaced it. It's okay. I remember most of it anyway. Yeah, let's try this one. This one's a little bit different. So y times cosine of y divided by x plus y squared equal to 1. All right, so yeesh. Yeah, that looks terrible. Actually, let me take a look at something really quick just to make sure I'm approaching this the right way. I just want to see one thing here. Yeah, okay, that's what I thought. So here's the thing. I know the other day I said like you don't typically want to multiply by a variable, but you can. You're not going to change your answer. It's just going to look different. So what I'm saying is, right, we could differentiate this as is. It's not nice, right? Do the bottom times the derivative of the derivative of the top. So I have to use the product rule here. Derivative of y is y prime times cosine of y plus y times, here's the derivative of cosine of y. Derivative of cosine of some stuff is negative sine of your stuff times the derivative of your stuff minus, then we do the other way, right? We did bottom derivative of the top. Now it's going to be the top times the derivative of the bottom. The derivative of the bottom is 1 plus 2y times y prime, all divided by the denominator squared. And I ran out of room. It's equal to the derivative of the right-hand side, which is 0. Okay, well, here's what's kind of interesting about this. Solving this, well, if you're setting a fraction equal to 0, you're really just setting the top equal to 0. So we can kind of ignore the denominator completely and say, well, really what I've got is x plus y squared. I'm going to factor out the y prime from here, right? So I've got x plus y squared times cosine of y plus, well, really minus, right? Because it's plus y times negative sine. So minus y times sine of y times y prime minus this. I am going to distribute this to each of these terms here. So it's going to be minus y cosine of y, and then minus y cosine of y times 2y prime. Equal to 0. Oh, this is terrible. But I've got my y prime. So here are my y prime terms. Here's one y prime term. Here's another one. So I'm going to leave those on the left. I'm going to bring everything else to the right. I really don't want to rewrite this again, but I guess I will. So from these terms, I will factor out a y prime. It's going to be gross. So I've got x plus y squared times this, which is cosine y minus y sine of y. And then I've got this, which is minus, I've got a y times a y, so it's a, and then 2. So it's a 2y squared cosine of y equal to this added over there, so y cosine of y. And finally, I really don't want to write it. You're going to have, he says before he writes it, this y cosine of y divided by all of this garbage. X plus y squared times cosine of y minus y sine of y minus 2y squared cosine of y. Okay, I was trying to make a point, which is you shouldn't do it this way. I feel like I've made the point somewhat in that this looks terrible, right? So at least it seems like maybe we should do something different. I wonder. Huh. That's interesting. Sorry, I'm seeing something that looks slightly different. Let me double check my work real quick just to make sure I haven't done something stupid. I'll double check. Because there's a different way of doing this, but the answer does look very different. Oh, I know why, because stupid stuff. Okay. Yeah, this is, so I'm sure this is fine. But let's check out a different answer. Because there is another way to do this. And what I really want to point out to you all is your answer is going to look very different. You have to kind of be okay with that. So here's another way we could do it. We can say instead of doing the crazy thing that we just did, we should make our lives easier. So I'm going to multiply both sides of the denominator here. And get y cosine of y equal to x plus y squared. And then we're going to differentiate both sides like this. So differentiating the left, we get y prime times cosine of y plus y times negative, let's make it minus, sine of stuff times the derivative of stuff equal to 1 plus 2y prime. Bring this over to the left and factor out a y prime. Y prime times cosine of y minus y sine of y, and then minus this is minus 2y, and then factor out the y prime. So then our answer here was much easier to get to. It's 1 divided by cosine of y minus y sine of y minus 2y. You might be asking yourself, is this actually the same as this thing over here? It is. It's just kind of crazy. I could try to show you if you want. Look, so let me show you one thing to make it slightly more believable. The way you try and make your answers look the same is you use this original equation. 1 is equal to all this. So I could rewrite this as y cosine of y over x plus y squared, all divided by this stuff here. And although this might not look exactly the same as this, we're definitely on the right path, right? Because I've already got y cosine of y on top, y cosine of y on top, and then I'm going to be dividing by x plus y squared. There's an x plus y squared times, oh yeah, times cosine of y minus sine of y, times cosine of y minus sine of y. Oh, it looks pretty good. Minus, there's probably something we have to do to fix this, but you can see, I think it's pretty believable at this point that these answers, although they look very different, if you use an algebraic manipulation, they actually are the same. So the bigger picture here is that don't do it the terrible way, right? If you're like, I have to do the quotient rule, no. If you're doing implicit, you should almost never have to do the quotient rule to start out with, at least. You should always be like, I'm just going to multiply everything so I don't have any fractions, and then take the derivative of both sides after you do that. So that's a good thing to actually believe, right? That you can manipulate an equation before you differentiate both sides and then make your life a little bit easier. Okay, let us shift. I don't really want to say shift gears because we're not really shifting gears. We are moving forward to talk about related rates. Related rates, what do I want to say about related rates? What I really want to say about related rates is there's a lot of chain rule in related rates. Actually, let me grab one other document here. Oh, why are you hiding from me? Sorry, I'm hiding stuff from myself. Where did you go? Excuse me. Yeah, I don't want you. Cool. So let's kind of start off with what I think of as the classic example. I think someone sent me one similar to this. I'm going to change the numbers slightly because I don't remember the numbers you sent me. Throwing a rock in a pond. You throw a rock in a pond and it creates circular ripples. And those ripples, right, the radius of the circles increases at a fairly linear rate. We'll just say it's linear. So let's say that the radius of the circular ripples, ooh, that's nice, increases at a rate of, I don't know, let's make it something like 2 feet per second, sure. And so you don't have to really draw a picture for this one. There are some situations where it's really necessary to draw a picture. This one, I'm going to kind of just say, well, let's think about what's going on. So we know, right, at time equals 0, so when the rock hits the water, your radius is 0, right? So you've got like, boom, swoosh, rock hits the water. And then when time equals 1 second, so after 1 second, the radius should be 2 feet. Okay, and then when time equals 2 seconds, the radius should be 4 feet. When time equals 3 seconds, I can't draw a circle that big here. The radius is 6 feet. And so on and so on and so on, right? So every second, the radius is 2 feet larger. We want to know a few things. We want to know how fast. I'm going to ask 2 different questions. Let's start with, I feel like area is the better question. How fast is the area increasing, right? We know it's increasing when the radius is 10 feet. And then let's also ask when it's 20 feet. Okay. So here's the setup I want you guys to think about. When you are doing a related rates problem, it is called a related rates problem because literally there are rates of change that are related to each other. In this problem, we're talking about the rate of change of the radius as it's related to the rate of change of the area. So those are the rates that are related. And the area's rate of change is directly related to the radius's rate of change. So let's write down what those things are. So when I'm doing a related rates problem, the first step
well, I should say the zeroth step is to draw a picture if we need to. I don't really think we need to draw a picture of a circle. The first step is to ask yourself, what is changing? With a fine lens, meaning, yeah, okay, lots of things are changing, right? Literally everything about the circle is changing. The radius, the area, the circumference, the diameter, right? There are lots of answers to that question. So really the question should be, what is changing that we care about, / that we know about? We know how the radius is changing. We're being asked about how the area is changing. So those are the two things that should actually be showing up in our answer to this question. We know that the radius is changing. And we also want to know how the area is changing. So usually there's going to be the things that we know, we should list them all, and the things that we want to know. The radius is changing at a rate of 2 feet per second. So we're going to write that as dr dt. Right? The radius is changing at 2 feet per second. So dr dt, the rate of change of the radius as time goes on, is 2 feet per second. We want to know how the area is changing. We want to know what dA dt is, the rate of change of the area as time goes on. We don't know that. That's what we're trying to find. I can be a little more specific. We want to know what dA dt is when the radius is equal to 10 feet. Or I think I said 20 feet was the other one. All right, so that's the first thing we're going to do is figure out what's changing. Or as my old teacher used to say, find the d what's. Right here we're finding the dr dt or the dA dt. Usually the bottom d what is going to be a dt because most of the time we're asking how something changes with respect to time. It's not always 100% true though. So there are other related rates problems where you're not talking about how things change as time changes. But mostly there are. I think there's a couple like pressure, volume, temperature things that you can also ask, like PV equals nRT equations that you can do, like chemistry stuff. I'm not great at chemistry, so yeah. All right, the second step, find an equation relating all the variables except for time, or except for whatever's in the bottom. So we want an equation relating the non-time variables. By the way, notice what is changing, that's the rates. So we got the rate of change of the radius and we're looking for the rate of change of the area. And now we're relating those things. We're not relating the rates yet, we're just relating the variables and then we'll relate the rates. So basically this point is you want an equation relating area and radius of a circle. Usually the answer to this question is some sort of geometric formula. For a circle, we know the area of a circle equation, it's area equals pi r squared. Usually it's going to be some sort of triangle, square, rectangle, cylinder, whatever, etc. Sorry, one sec. My wife is asking for the last 4 of my social. She thinks she would know by now after being married for 13 years, but okay, whatever. Anyway, so area equals pi r squared. This third step is the place where people often have a challenge. We're going to differentiate both sides. We're going to differentiate both sides with respect to time or whatever the bottom part of your derivatives are. So differentiate with respect to time. That's what WRT means, with respect to. Okay, so if it's helpful, I'm going to write this in a slightly different way for 1 sec. We can think of this, if you want, as area is a function of time, right? Both the area and the radius of the circle depend on how much time has passed, right? When time is 0, the radius is 0. When time is 2, the radius is 2. When time is 4, the radius is, sorry, when time is 2, the radius is 4. When time is 3, the radius is 6. And we could also find the areas if we really wanted to, right? The time equals 0, the area is 0. When time equals 1, the area is pi r squared, so 4 pi.
The time equals 2, the area is 16 pi. And at time equals 3, the area is 36 pi. Wow, yeah. Also notice, right, the area the rate of change of the area is really dependent, right? In the first second, the area increases by 4 pi. In the second second, the area increases by 12 pi. In the third second, the area increases by 20 pi. So every second, the area is increasing by more and more each time. So I'm going to write this as, well, area is a function of time, and the radius is also a function of time. Now we're going to differentiate both sides. So the derivative of area, so this part, I feel like people sometimes have a hard time with. We're just going to say that that's the derivative, a prime of t. Okay, chain rule time. What's the derivative of some stuff squared? Oh, it's 2 times your stuff to the first power times the derivative of your stuff. Now, people, for whatever reason, don't usually write it this way. Instead, what they do is they write the same thing just with different notation. Usually for related rates, we almost always use the Leibniz notation, which is the dr dt or the dA dt. So, and I'm going to differentiate both sides. What I'm going to get is, so the derivative of a is the derivative of a, which is dA dt, equal to the derivative of pi r squared is pi times the derivative of r squared is, well, the derivative of some stuff squared is 2 times your stuff to the first times the derivative of your stuff. And the derivative of r is dr dt. Just like when you're doing implicit differentiation, the derivative of y squared is 2y times dy dx, right? Your variable here is a function of a different variable. So when you differentiate it, you have to then multiply by the derivative of the inside part. You have to use the chain rule or use implicit. They're the same thing, really. Okay, so here's what should happen when you're doing something like this. After you differentiate both sides with respect to time, the thing you want to find should show up. And the thing that you know usually, although not all the time, there's a couple things where this doesn't show up, but usually that should, that should always show up as well. Sorry, I'm thinking of something else. So now we're going to plug in all the things we know and solve for what we want to know. I probably can squeeze this in up here. So, yeah. Okay, so we're going to plug in, I don't know dA dt, that's what I'm trying to find. I'm going to get dA dt again. dA dt is the rate of change of area with respect to time, so how fast the area is changing at any given moment. And it's equal to 2 pi times the radius, which I'm going to plug in 10 feet for the first one. So times 10 feet. Usually I don't plug in the units to the end, but I'm plugging them in now. Times dr dt, which is 2 feet per second. So multiplying this out, I get 2 times 10 times 2, which is 40 pi. I get 40 pi. Feet times feet per second is feet squared per second, which makes sense, right? Because area should be changing as a unit squared per a unit of time. So when the circle has a radius of 10 feet, the area is increasing at 40 pi square feet per second. If instead it was when it was 20 feet, then, so right, when r equals 20 feet, I'd have a 20 there instead of a 10, and the area would be increasing at 80 pi square feet per second when it's 20 feet in radius. So, right, and it makes sense if you think about it, right? If the radius itself is increasing the same amount every second, well, right, when the circle is small, the radius increasing by some amount doesn't get you a whole lot more area. But when the circle is big, the radius increasing by the same amount, right, that's going to get you a whole lot more area. So the same increase in radius makes a much, much bigger difference if you've already got a very big circle, which is why when the radius is bigger, the increase in area is a lot more, even though the radius is increasing by the same amount. Okay. The other question I wanted to ask, but I didn't, okay, cool. So the other question I wanted to ask is, how fast is the circumference increasing? So how fast is the circumference increasing? Circumference. At the same moments. Okay, well again, we're going to do the same thing. We already know what dr dt is. So dr dt is still 2 feet per second. And now we're interested not in the area, but the circumference. And the equation for circumference is 2 pi times the radius. So that's just, sorry, I kind of got ahead of myself there. Sorry, let me stick to the plan. I also want to write down, I want to know how the circumference is changing at a particular moment. So then we write the equation relating the non-time variables. Circumference equals 2 pi times the radius. Then we differentiate both sides. The derivative of c is the derivative of c, right? dc dt. The derivative of 2 pi r is going to be 2 pi, right? The constant multiple hangs out. And the derivative of r is the derivative of r, right? It's not just 1, it's dr dt, right? The derivative of r isn't 1, right? Because dr dt isn't 1 foot per second. The derivative of r is dr dt, which actually is going to be 2, but right, I want to point out, right, the derivative of r is not just 1. It is 1 times dr dt. So then we plug in what we know, solve for what we don't. So I'm plugging in, I don't know this, so dc dt equals 2 pi times, r is 10 feet, but there isn't anywhere to plug that in, right? So I'm just plugging in dr dt, and I'm going to get, so here's something kind of interesting. No matter how big the circle is, whether it's got a radius of 10 feet or a radius of 20 feet, there wasn't anywhere to plug that in, which means it's inconsequential. So if the radius is increasing at 2 feet per second, the circumference is always increasing at 4 pi feet per second, which kind of makes sense if you think about it, because the circumference is just a multiple of the radius. So essentially, if something is a multiple of something else, their rates of change are directly, they're multiples of each other. Whereas if something is equal to some higher power of another variable, then how this changes is not directly proportional to how this changes. It's going to change much faster. But yeah, sometimes you'll see that, oh yeah, if the radius is changing at some amount per second, then the circumference is just changing at 2 pi times that amount. So something to be aware of. Yeah. All right, let's do some more. So this process is going to be like the same every time. We're going to ask ourselves what's changing, find an equation relating those things, find the derivative of both sides with respect to time, usually, and then try and solve for what we want to solve for. So look at this next one. Oh, yeah. I feel like this one is kind of, yeah. I'm gonna come back to that one. Come back to that one. Sorry. Let me go over here. Let's do that. Oh, why is my? I think I might need to charge my mouse. Sure. Let's look at this one. So Gabriella, Grant's daughter, is standing. These kind of take a little bit to write out, so I'm writing that. Gabriella is standing 6 feet from her sister Mia. Who was holding a balloon, but she lets it go. So the question we're going to ask is, if the balloon is rising at a constant speed of 2 feet per second, so if the balloon rises at a speed of 2 feet per second, how fast is the distance between Gabriella and the balloon changing? Right. How fast is the distance from Gabriella to the balloon changing? Now, I haven't said enough yet, right? Because I don't know where the balloon is, and it's going to be a different amount depending on how far away the balloon is. So changing after 4 seconds. Okay, we definitely need to draw a picture here. So here's Gabriella. Here's Mia with the balloon. They are 6 feet away from each other. That distance isn't changing. But then, here's Gabriella and here's Mia. But then Mia lets go of the balloon, and the balloon starts going up. That's my balloon. It's not a very good balloon. And so this length here, that is changing. So things that are changing in our picture, we want to give them variable names. You could call this H or Y or whatever letter you like. I usually like H for height. And then what we want to know is how fast the distance between Gabriella and the balloon is changing. So I want to know how this is changing. I'm going to label this. Usually for diagonal distances, I use the letter S. We almost never use the letter D, because we don't want to write D, 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 T. It just seems weird. So let's write down what's changing. We know that H is changing. And the rate of change of H is dH dt. And it is equal to 2 feet per second, because that's how fast the balloon is rising. We also know that S is changing. We don't know how though, right? That's what we're trying to find. We want to know what ds dt is. So that's the setup. Well, that's not the setup. That's what's changing. And then we need an equation relating those things. So again, most of these equations are going to come from some sort of geometric formula. In this case, I've got a right triangle. I'm going to use the Pythagorean theorem. That 6 squared plus 8 squared equals s squared. So our equation is 6 squared plus h squared equals s squared. All right. Here's what's nice about this. We don't have to necessarily write our equation so that something is totally a function of something else. Right? You don't have to get s as a function of h or h as a function of s, just like we did have a as a function of r here. Because we know how to do implicit differentiation. So instead of trying to write like s equals the square root of 6 squared plus h squared, that would be silly. We're just going to differentiate right away. And that's always going to be the case. You're never going to want to, I mean, with a couple rare exceptions, you usually just want to leave that alone and differentiate. Sometimes there is some simplifying you can do, so you don't have to do like the quotient rule or something, but usually you're just going to differentiate straight away. So let me ask you guys, what's the derivative of 6 squared? It is 0, right? It's not 2 times 6. It's 2 times 6 times the derivative of 6, which is 2 times 6 times 0. Or just 0, right? Because that's 36. The derivative of constant is 0. The derivative of h squared, or some stuff squared, is 2 times your stuff to the first power times the derivative of your stuff. The derivative of s squared is 2 times your stuff times the derivative of your stuff. Something to be aware of.
you need these things to show up after you differentiate. If these aren't showing up, you've got a problem. Something else to be aware of. You don't want to plug in anything until after you have done the step where you differentiate both sides. So, right, you don't want to plug in right here that h is 8 feet high, because that's not going to be helpful, because then you're just going to get 0 when you differentiate both sides. So we've got this equation. If you wanted to, you could divide both sides by 2 and just get h times dh dt equals s times ds dt. So now we do need to plug in what we know to find out what we don't. So we're looking for this. So whatever you're looking for, you should be able to substitute in for everything else. So I know I erased all the information here. So now we do need to figure out what values are equal to what. So I know, let's see, I don't know anything really. I know dh dt is 2 feet per second. So I've got, so I'm going to write the equation again. So I know that I've got 2 feet per second here. But what's h? Well, I know I erased it, but we said we want to know how things are changing, how this distance is changing 4 seconds after the balloon has been released. Since the balloon is traveling at 2 feet per second, after 4 seconds, it's going to be 8 feet high. So at time equal to 4 seconds, we have that the height is 8 feet. So that's going to be 8 feet here. And then on the right-hand side, we should also be able to plug in for s. So here's the thing. We actually have to use this equation and plug in 8 for h, and then we can solve for s. So we have 6 squared plus 8 squared equal to s squared. That's 36, that's 64. Add together, you get 100. So s is 10. Not plus or minus 10, because a negative 10 wouldn't make sense. It's just 10. Now, I will point out, a lot of the time when you're dealing with a right triangle like this, people are going to try and make the numbers nice for you. Web work won't, but real people will. And this is a 3, 4, 5 triangle just multiplied by 2, right? This is a 6, 8, 10, which is just a 3, 4, 5, and you multiply everything by 2. So there's a lot of Pythagorean triples where the numbers are nice. 3, 4, 5, 6, 8, 10, 5, 12, 13, lots of other things, 8, 15, 17. Those are all examples of 3 sides of a right triangle that work out nicely. Anyway, solving for ds dt, we're going to get 8 times 2 divided by 10. Notice that the units work out, right? I'm going to get ds dt equal to 8 feet times 2 feet per second, so 16 feet squared per second divided by 10 feet. The feet cancel, and I get 16 over 10, so 1.6 feet per second. I will say, I usually don't write the units in until the very end, meaning what I actually would have done if I was doing this is I would have written h is 8 feet, dh dt is 2 feet per second, s is 10 feet. I'm solving for ds dt. I do the division, I get ds dt equal to 16 over 10, which is 1.6. And then I ask myself what units make sense. I'm asking how a distance is changing. So I want to know how fast or how the feet are changing per the unit of time. So it's feet per second. So if it's a distance, it's just your measure of distance per unit of time. If it's an area, like in the previous problem, I think it's still up, yeah. When we did an area, the rate of change for an area was our unit squared per unit of time. And if it was a volume, it should be your unit cubed per unit of time. So we're talking about the length changing, it's feet per second, or miles per hour, or meters per second. If it's an area, it's feet squared per second, or miles squared per hour, or right, it's your unit squared per unit of time. If it's a volume, it's your unit cubed per unit of time. Yeah. So if you're trying to figure out what the units are, think about the dimensions. Are you talking about a length, an area, or a volume?
Let's look at a different example. This example, I feel like, sure, where'd you go? Example, I feel like is maybe a little less usual, but still is applicable. So let's do it. So let's say the radius of a cylinder is increasing at 3 inches per second. 3 inches per minute, sorry, not second. And the height is decreasing at 4 inches per second. Minute, 4 inches per minute. Let me make sure I got this right. Yeah. How fast is the volume changing? When the radius is 8 and the height is 5. All right, so we know what's changing. What's changing? We know that the radius is changing. So I suppose I should draw a picture. Okay, fine. Just that. Wow, that's a big circle. It is good to draw a picture. So the radius is this, the height is this. So we know how things are changing. The radius is increasing at 3 inches per second. So dr dt is 3 inches per second. I'm just going to write 3. And we know how the height is changing. The height is decreasing at 4 inches per second. So we're going to write that dh dt is -4. When something is decreasing, its rate of change is negative. And finally, we want to know how the volume is changing. And here's what I already know before doing anything. If I'm trying to find how the volume is changing, my final answer is going to have units that are inches cubed per minute, right? If we're measuring in inches per minute, our volume is changing in inches cubed per minute. Okay. So now I need the equation relating the radius, the height, and the volume. So that's going to be, well, the volume of a cylinder is the base area, which is the area of a circle, which is pi r squared, times the height. Now, this example is kind of different than most examples because most of the time with a related rates problem, you're trying to get it down to just 2 variables. The one you want to know how it's changing and the one you know how it's changing. This is kind of an exception. Well, I'll show you a different problem which looks similar but is different after this. So we're going to differentiate both sides. Derivative of volume is the derivative of volume. I think that sounds dumb to say, but it is. Pi r squared h, the derivative here, we're going to have to use the product rule. So I'm going to think of this as pi r squared times h. The derivative of pi r squared is 2 pi r times dr dt. Right, the derivative of pi times stuff squared is 2 times pi times your stuff times the derivative of your stuff. Times the other thing left alone, right? So there's your derivative times your not derivative, and then you flip it. Plus, right, product rule, you have to have a plus sign in the middle. Leave this alone, pi r squared, multiplied by the derivative of h, which is just the derivative of h. So I want to re-emphasize to everybody, if you're taking the derivative of a single variable on its own, derivative of a variable is the derivative of that variable. Okay, now we're going to plug in for everything. We should be able, I think we're given everything here. So we're going to get, let's see, 2 pi times, we're given that the radius is 8 inches. We know that dr dt is 5 inches. Sorry, dr dt is 3 inches per minute. And the height is 5 inches. I do want to point out, right, this is giving me, so I just want to say,
right? I'm getting 8 inches times 3 inches per minute times 5 inches. That's inches times inches times inches per minute. So it's inches cubed per minute. So the units are right. You don't need to write them in until the end though. Plus pi times r squared, r is 8 inches, times dh dt, which is negative 4 inches per minute. And let's see, multiplying this all together, 5 times 2 is 10, 8 times 3 is 24, 24 times 10 is 240. So you're getting 240 pi minus, there's a minus there, 4 times 64 is 256, so 256 pi. So we're getting negative 16 pi inches cubed per minute, which means the volume of this is actually decreasing. So you can either write your answer as dV dt is negative 16 pi inches cubed per minute, or if you wanted to write more words, you could say the volume is decreasing at 16 pi inches cubed per minute. And you don't have to write the negative then if you say it's decreasing. But you could say it's increasing at negative 16 pi cubic inches per minute, or you could say it's decreasing at 16 pi cubic inches per minute. Yeah, so sometimes things decrease. We got time for one more. We'll do more of these next week, maybe. Yeah, we'll do a couple more next week for sure. But then we'll probably have something else to move on to. All right. Yeah. So I will also point out there are more examples of these on Grant's website. So just so everybody knows, right? If you look at this website here, if you look at that, if you look at problem solving 6, so PS6 PDF, there are solutions there. So if you want more example problems that have solutions written up so you can practice them, they are available for you. I highly encourage you to check them out if you're looking for more resources. But let's do this last problem here, which this is definitely a very standard type of problem. Yeah. So water is being poured into, I don't want to write this all out. I'm just going to say the words and we'll draw a picture. So water is being poured into a conical tank. Usually we assume for a cone-shaped tank that it's point down, right? So here's my cone-shaped tank. Occasionally it might be shaped the other way. Also, you might see problems where like they're pouring dirt or gravel into a pile and it forms a cone. In that case, the cone is pointing upwards, right, where the tippy point is at the top. But conical tank seems like it makes sense to have the water like opening this way. So water is going in, and let's see. So it's being poured into a conical tank at a rate of, so water goes in at a rate of 3 cubic feet per minute. And we're given that the tank has a radius of 3 feet and a height of 12 feet. So the radius of the tank is 3 feet, and the height of the tank is 12 feet. And we want to know how fast is the water level rising when the water is 6 feet deep. I'm going to change that. When the water is 5 feet deep. Numbers probably won't work out quite as nicely. That's okay. All right, so let's check this out. Let's draw the water. So here's the water. And the water level is rising. So even though I want to know what's happening when the water level is 5 feet high, I'm going to say that the water level height is given by just h, because it's changing. And things that are changing should be given variable names. So here's what I know. And so again, I'm going to walk through my usual setup, right? I want to identify the things that are changing. Well, I know how the volume is changing, right? I'm putting in a volume of water at 3 cubic feet per minute. So I know that dV dt is equal to 3 cubic feet per minute. And I want to know how fast the water level is rising. I want to know what dH dt is. A couple things to make note of. It should be positive, right? Because h should be getting bigger as the water level rises. And it should be measured in feet per minute because it's a measure of length, not of area or volume per unit of time. Okay, so then we need an equation relating the volume and the height. And here's the problem. The equation for the volume of a cone, right, whether it's the big cone or this smaller cone, right here. All right, here's my smaller cone in red. The smaller cone, the volume of that cone is still the volume of a cone, which is 1/3 pi r squared h. So there's my radius, there's my height. Now here's the thing. I know how volume is changing. I want to know how height is changing. I don't give a damn about the radius. Unlike the previous problem, right? The previous problem, they're like, oh yeah, the radius is changing this way, the height's changing this way, use them both. But most of the time, especially when you're dealing with a cone, you're going to be given something like the volume, the rate of change of the volume, asked how the height's changing, and the radius is kind of in the way. So here's what's great about cones. The radius and the height are always proportional to each other. In fact, you can use the big cone to see what they are. I can see that the radius is 3 feet and the height is 12 feet. So the proportion of the radius to the height is 3 to 12, or 1/4. So it makes sense, right? This radius of 3 feet is literally 1/4 the radius of the height of 12 feet. And then since I want to write this without the radius, I'm going to solve for the radius. So the radius is 1/4 the height. If you don't love this explanation, that's fine. You can do it a different way by using similar triangles. So if I draw my cone again, so here's my big cone. Here's the triangle I actually want to draw, where the radius is 3, the height is 12. And then if I draw my smaller cone, right, which has a radius of r and a height of h, well, this smaller triangle is similar to the bigger triangle. And so you can say, oh yeah, the base to the height for this triangle equals the base to the height for that triangle. Oh, it's the same thing. So you can totally use similar triangles, but usually it's easier just to be like, hey, look, in this cone, I know the radius is 3 and the height's 12, so the proportion of the radius to the height is 3 to 12. Totally works every time. So then we're going to rewrite the volume as 1/3 pi times 1/4 h, or I'm just going to write h over 4 squared times h. And then before you differentiate, we should simplify this because you can multiply it out and get 1/3 pi times h squared over 16 times another h. And then the 1 over 16, let's multiply that by 1/3 and get 3 times 16 is 48. So I've got pi over 48 times h cubed. That's going to be much easier to differentiate both sides of. So now I differentiate both sides. I know we're almost out of time here. You get dv dt on the left. And on the right, the constant hangs out. You get pi over 48 times the derivative of some stuff cubed is 3 times your stuff squared times the derivative of your stuff. And now we're just going to plug in to solve for dH dt. So I'm going to erase this picture because I need room. This is the only place I've got room. So plugging in what we know dv dt is 3. 3 over 48 reduces to 1/16, pi over 16 times h squared. Well, h is 5 feet deep times dH dt. So then you would solve for dH dt. So 3 equals Pi squared times pi is 25 pi over 16 dh dt. So you multiply by the reciprocal, you get 16 over 25 pi times 3 is dh dt. Or multiplying that, you get, sorry, I know like it's, I know yes, I know this looks kind of ugly. You're going to get 48 over 25 pi feet per minute. Okay, what you should take away from today is the process. Identify what's changing, both what you know and what you don't know, usually, or I should say what you know and what you want to know. Find an equation relating, hopefully, only those variables. In a cone, you're typically going to have to replace the radius with something in terms of the height. After you've written your equation, differentiate both sides. After you have differentiated both sides, plug in the things you know, solve for the one thing you don't know.